Okay. Close enough. So, we're asking how does chemical configuration at the alpha carbon impact which face the nucleophile attacks. This is a good chance to review what we talked about earlier on with stereochemistry. If you've got a stereocenter at the alpha carbon, then those two faces of the ketone are what kind of faces? Homotopic and antiotopic or diastereotopic? That's not rhetorical, you get to actually answer. If you've got a stereocenter at the alpha carbon, are the two faces of the ketone, top face and bottom face, homotopic and antiotopic or diastereotopic? Diastereotopic, yep, because, I mean, the simplest way to see it is that if you attack from the top face versus the bottom face, you're going to get diastereomers of each other, all right? So various people have developed models for trying to sort of predict based on structure which diastereotopic face of the ketone will be preferred. There are three models presented. The only one we're going to talk about is the so-called Falcon-On model, named after the folks that proposed it. And it works pretty well. The idea is that we're going to sort of take the Newman projection view down this bond between the carbonyl carbon and the alpha carbon. So carbonyl carbon's going to be in front. So now the two diastereotopic faces of the ketone are on our left and on our right. And then we're going to draw that stereocenter in the back. Now, as I've drawn it here, it looks like that large group is basically eclipsed with the carbonyl group, and the small group, we sort of lean our faces in the plane of the page and look that way. The small group should be coming out of the page to our left, and then the medium group should be coming out towards our right. Now, what we are not going to do is worry about which conformation is most stable. Remember from our chapter on kinetics, we have this Curtin-Hammett principle that suggests that as long as the barrier to rotation around this bond is relatively low and the conformations are all sort of in equilibrium with each other, what matters is not which is most stable, but which orientation of attack is easiest or most favorable. And so that's what this Falcon-On model tries to predict. So there's some basic principles. You want, in general, the large group perpendicular to the carbonyl group and anti to, or opposite, maybe not, maybe anti is the wrong word because that sort of creates the expectation of exactly 180 degrees from, opposite the incoming nucleophile. And there are two reasons for this. Reason one is sterics. You want the larger group to be out of the way. And then reason two is a hyperconjugation effect. So there's two ways to see this, and perhaps depending on context and identity of the groups, one way will be more important than the other. Let's just actually draw the large group. Let's see if we rotate this large group down, that would put what, medium group here versus small group there. Ultimately, by the way, we're going to be considering two different possible orientations. One in which the large group is perpendicular to the left, and the other in which it's perpendicular to the right. But for right now, let's just focus in on this one. And imagine a nucleophile approaching opposite the large group. Okay. Nucleophile is going to be coming in. Now, as the nucleophile attacks, you're going to have pi bond breaking, sigma bond forming. Notice I'm having the nucleophile approach from the Bürgi-Dunitz angle. We haven't necessarily talked about that. That's an aspect later on. But I want you to consider, as we're forming we're newly forming a sigma bond, but that means sort of opposite the sigma bond, we're also forming a sigma star. Okay? So I'm not sure how to represent this. We'll just do and I'm only going to draw that part of the sigma star. There'd be another part of it here behind the nucleophile, but I'm not going to draw that if that's okay. Okay, fine, I will draw it. And I won't use, I don't know, the dotted gray is actually quite distracting to me, so now we got to use color. But since it's, how do I change the thickness of the line? I've asked this before, and, oh, there it is. Okay, you have to scroll. All right, we'll just use gray. Bloop. Okay. So, you have what in the red dotted line represents the newly forming sigma bond between carbon and the nucleophile, and then this is the newly forming carbon nucleophile sigma star. Another word that you will hear chemists use for things that are in process of forming, a couple of different words you will hear is incipient, which sounds sinister somehow to me, and also nascent, from the either Latin or Greek, I'm not sure, root for being born. Spanish speakers, you talk about the birth of Jesus is the nacimiento, nascent. Maybe, no, not familiar. Vaguely familiar. Yeah, you've said those words before. Okay, so in gray is the nascent or newly forming sigma star. And with the red dotted line, we're not drawing the orbital, but we can imagine it there, the newly forming nascent carbon nucleophile bond. Okay? So there's two possible things to consider here. One is hyperconjugation involving the sigma bond between the alpha carbon and the large group, donating to the nascent or incipient carbon nucleophile sigma star. So that's one effect. The second effect is donation of the nascent or incipient carbon nucleophile sigma bond to the sigma star between the alpha carbon and the large group. Okay? For the most part, and you could imagine that either of these two could be stabilizing. So let's talk about when donation to the nascent sigma star might be stabilizing. Okay? Early on, as the nucleophile attacks, the bond isn't very well formed. And if the bond isn't very well formed, that means the sigma star is pretty low in energy. Okay? So early on, prior to attack, or early on as the attack is happening, that sigma star is a good acceptor because it's very low in energy. And in that case, it might not matter. Sterics may be the dominant factor, right? If these are all, if we haven't really talked about what kinds of bonds these are between the alpha carbon and the large, small, and medium groups. But early on in the class, we talked about what kinds of sigma bonds make good donors, right? And in general, they are bonds between carbon and hydrogen or carbon and carbon, okay? It's generally not a thing to worry about, oh, is the large group a better donor than the small group versus the medium group if they're all basically carbon-carbon bonds. In that case, the major thing is probably sterics. However, there is a variation of Falcon-On if where I guess maybe we'll just put a stay tuned by this one because it will make sense probably to show you how this plays out and then show you this variation. So stay tuned on the idea of the nascent carbon nucleophile bond stabilizing the alpha carbon to large group sigma star. This is thought of usually only in select cases, and I'll show you one of those. Okay, so the two factors that govern why we think the large group needs to be perpendicular to the carbonyl is so that it can be as far away as possible from the approach of the nucleophile, and so you could take advantage of hyperconjugation involving the carbon large group bond as a donor, donating to the low-lying sigma star of the nucleophile as it approaches. All right, so you've got both of those. We've got the conformation on the top approach from the right-hand side, and then we'll do something similar approach of the nucleophile from the left-hand side. Again, you've got this. I'm not going to draw the hyperconjugation happening here. You can imagine it by analogy to what's sort of going on before. But again, we're going to say that we approach mostly consistent with the Berge-Dunitz angle. Okay? Now, look at these two. Which do you think is lower in energy? If we approach from the right, the Berge-Dunitz trajectory brings the nucleophile sort of pseudo-eclipsed with this small group. If we approach from the left, the Berge-Dunitz trajectory brings us pseudo-eclipsed with the medium group. So which approach do you think is lower in energy?
Top one.
Yep, top one. This is probably the lower energy approach. You're eclipsed with the small group versus the medium group, okay? And so the predicted favored product is going to be the one that comes from attack from the right-hand side, and we can, sort of just adjust our Newman projection. We can put the nucleophile here, the R group here, and then the negatively charged oxygen there. If we were to draw the favored product sort of from the side, from our perspective, the nucleophile came in from looking at it sort of from this direction, our nucleophile came in from the right-hand side. Remember, we're leaning our heads into the page, looking at down this carbon, carbonyl carbon to alpha carbon bond. So from that perspective, our right-hand side is actually underneath the page. Do you see that? Looking down that bond, here's the Newman projection. My right-hand side is inside the page. So that would mean that the favored product is one in which the nucleophile comes in from below. And I'm just drawing that stereocenter exactly the same as we drew it previously. I'm not attempting to, yeah, okay? So this is the favored diastereomer, the one in which my nucleophile adds from below. Okay, so that's sort of the Falcon on model. Your text doesn't say anything about how well it works in terms of predicting percentages. I don't think it does predict percentages, but you can use it to predict major versus minor diastereomer. Okay.
I think your small and medium group are swapped.
They're not. Yes, they are. Thank you. Relative to how they were here. Thank you. Another thing that may be troubling you is I have not bothered to draw that alpha carbon stereocenter in exactly the same way that it's drawn in the Newman projection. If I keep the stereochemical configuration from here the same, where small is coming out of this and medium is going back in, that's correct configuration, though it may not. Fine.
Does it slow synergy when it's eclipsed?
Well, let's see. As drawn here, the nucleophile is opposite the large group. And the medium group is anti to the R group, which means the small group is here. Those are both the same compound. I've just rotated the bond to try to make it more consistent with the Newman projection. Okay, so that's an example of the Berge-Dunitz angle's impact on how people think about stereoselectivity of carbonyl additions, and you can use this to try to have an idea of whether you can use this to try to predict what the major diastereomer should be. People, I do think they think about this when they're proposing syntheses of compounds, and so as you see reactions involving carbonyl additions, and oh, this is the major diastereomer, and yay. Probably along the way, as somebody was designing the synthesis, they thought about this kind of thing. Yeah.
So just to clarify, for B, like 1B, it's like the hyperconjugation effects. That's
Yeah.
the same for both sets of attacks. The only difference is the
steric
sterics.
issues. Yep.
Okay.
Right.
So both of those have the exact same hyperconjugation.
That's right. The major issue is which Berge-Dunitz trajectory is less hindered. Right. Yep. Good. Yeah.
So, in determining which groups are largest, I imagine there are both like steric and electronic effects, right? Because
Yes. Right. So, and the selectivity will clearly be determined and influenced by how much of a difference there is between large, medium, and small. You could imagine if M and S are both similar size, then trajectory A versus, we're using A and B far too much, so trajectory 7 and trajectory 8, that's going to be really confusing for people. Who cares? I'm sorry. Still got a bit of a cough. Right. If M and S are similar in size, then the trajectories 7 and 8 are going to be similar in energy, and then the selectivity won't be very good. But remember, it doesn't take a huge amount of energy to generate a fair amount of selectivity. The thing that Dr. Michaelis says is 1.4 equals 10. If your difference in energies for those two different trajectories is 1.4 kilocalories per mole, you got a factor of 10 in selectivity. And so, and remember the steric factors that we're dealing with, eclipsed interactions are often, on the order of 1 to 2 to 3 or more kilocalories per mole. So these effects can have an impact. All right, let me show you an example of a variation on the Falcon-On model. This is a compound that's going to have real things attached to it instead of small, medium, and large. Here is a methyl group. Here is a hydrogen. Guess which one is the small one? And then here is a nitrogen, and it's doubly benzyl protected. So benzyl equals that, right? So there's two of them. All right. So sterically, this works in terms that you would call this the large group, this the medium group, and this the small group. But there's another reason besides sterics that you would want to have that nitrogen perpendicular to the carbonyl group. So let's again put our noses in the plane of the page and sort of look down the bond between carbonyl carbon and alpha carbon. Let's put that nitrogen here. If we do that, sorry, we got to do this in stages or else we might get it wrong. As currently drawn, the nitrogen is eclipsed with the oxygen, right? And then hydrogen would be here, and methyl group would be there. Does that make sense? What?
Hydrogen is pointing at us, so it should be on.
Okay, very good. This is why we work together. We build a model. Is that right now? Yes. Okay. So we're basically going to be considering two different trajectories, 1 and 2. The first one will have the nitrogen here. That's not butyl, that's benzyl. If we do that, methyl group will be here and hydrogen will be here. Trajectory 2 would have the nitrogen on the opposite side with methyl here. That's a terrible 3. And then hydrogen here. So we are essentially talking about the difference between the nucleophile attacking this way versus this way. Okay, and already, I mean, you can see that trajectory 1 is the good one because it keeps the Bürgi-Dunitz angle. The Bürgi-Dunitz trajectory has the nucleophile pseudo-eclipsed with a hydrogen, which is better than being pseudo-eclipsed with the methyl group. Okay? Now, aside from sterics, there's one other reason why you would want the nitrogen anti to the incoming nucleophile. And going back above, do you remember I said that another option that you can consider is an interaction between not the sigma star, not thinking about the sigma bond and the sigma star of the nucleophile, but actually the carbon nucleophile nascent sigma bond and the sigma star between the alpha carbon and the large group. Okay? The reason why this is probably the biggest effect and it equally favors both of the conformations, but it's the biggest effect in keeping the large group perpendicular. That's a sign from geometry that means perpendicular to the carbonyl. Is probably this kind of hyperconjugation. The reason we're not thinking about donation of the carbon-nitrogen sigma bond into the nascent sigma star associated with the carbon nucleophile bond is because carbon-nitrogen bonds are lower in energy, so they're not great donors. And we're learning about that way on earlier in the course. Okay, the lower in energy a bond is, the less likely it is to be a good donor. This is the principle behind the Gauche effect that we learned about. But what goes around comes around in terms of electronegativity. Electronegativity lowers, rising tides lift all boats. Electronegativity pulls all orbitals down. So a sigma and a sigma star for a carbon-nitrogen bond are both going to be lower in energy because of electronegativity. And so probably the major effect here is you've got carbon, nitrogen, the alpha carbon to the nitrogen sigma star, which is low in energy and a good acceptor. And so, and we can draw that orbital. There would be a node here, a lobe there, another lobe there. I guess we, oh, nope, wanted the highlighter. There we are. Then we would talk about sort of this being the new sigma bond between carbon and the nucleophile, and it's probably donation from that carbon nucleophile bond into the carbon nitrogen sigma star that makes that conformation most reasonable. Okay, so you can sort of see there's two different ways of looking at it, and which you choose as the most reasonable way of looking at it is going to depend on context. Above, the major impact was sterics, and then in terms of electronics, we were thinking about donation of the adjacent sigma bond between alpha carbon and large group into the incipient or nascent carbon nucleophile sigma star. Here we've got the same conformation preferred, but the explanation that's most reasonable in addition to sterics is probably not thinking about using this sigma bond as a donor, but rather using this sigma star as an acceptor for the electrons in the newly forming carbon-nitrogen bond. All right. And then again, if you were to predict, proper what the favored stereoselectivity would be, the favored diastereomer here is going to be the one that has the nucleophile coming in from the right-hand side. And then we had the benzyl, doubly benzyl protected nitrogen there, methyl group here, and that would be our desired product. Yeah. And let's see, we could actually draw what that is after. If in this case, let's see, the nucleophile, well, we don't actually need to worry about what the nucleophile is. Oxygen is here, nucleophile is here. And then from our perspective, the nitrogen, I keep wanting it to be butyl instead of benzyl. Don't know what's going on there. Nitrogen, let's see, anti to the proton is methyl group, and that would put the hydrogen there. Okay, and that'd be the predicted favored diastereomer. Notice that this is an example of diastereoselectivity. The stereocenter adjacent to the carbonyl affects the new stereocenter that forms at the carbonyl. And this is a kind of, it's diastereoselectivity. It's something you don't need a chiral catalyst for. You've already paid for the chirality in the stereocenter that you incorporated at the alpha carbon. So you'll see people do reactions all the time where the stereochemistry of an adjacent stereocenter strongly influences what happens next door for a carbonyl attack. All right. So haven't had enough of carbonyl additions. There's a few other similar sorts of effects that your text talks about that are sort of worth exploring. But before we move on, any more questions about the Falcon-On model for predicting carbonyl stereoselectivity of carbonyl additions? Okay. So the next example brings together a lot of these similar effects and some questions of thermodynamic versus kinetic control, which is a useful principle to talk about. So one observation to begin with is that cyclic ketones, particularly cyclohexanone, reacts 300 times faster in lithium aluminum hydride reduction than the corresponding acyclic counterpart. Okay, so why might that be? Why might this react faster? Than an acyclic molecule. And to see this, we need to sort of zoom in on these carbons that are alpha to the carbonyl group. And you can sort of see it from here, but if we draw an actual Newman projection, here's that carbon in the front. There's that axial, that alpha carbon in the front. You've got an axial down proton, an equatorial up proton, and then the rest of the ring here. In the back, you've got something that's sort of neither axial. It's an sp2 hybridized carbon, the carbonyl carbon, instead of an sp3 hybridized carbon. So the best way we can draw that is kind of like this. Okay. The dihedral angle between the equatorial proton and the carbonyl group is around 4. So this is pseudo-eclipsed, which if you remember from, and we maybe didn't put too much of a number on this, but you've got two different eclipsed interactions here, and together two pseudo-eclipsed interactions between the alpha carbon CHs, equatorial CHs, and the carbonyl group. And together those are worth about 4 kilocalories per mole of destabilization, which means that the cyclic ketone is about 4 kilocalories per mole higher in energy than the acyclic ketone, which should explain why it reacts faster. Yeah.
I don't know if this holds any importance, but I was just noticing that like the 4% plus the other 105% that we have for the nucleophile attack adds it's like 109, which is kind of like the angle of a tetrahedral, right? Is that like a coincidence? Or?
I think that's coincidental. I think that's coincidental. The 105 is the Berge-Dunitz angle, which was calculated based on crystal structures, and not all of them were cyclic ketones. So yeah, I'm not totally sure what's going on there. So that's one thing to sort of keep in mind for cyclic ketones, that you've got these pseudo-eclipsed, especially in six-membered rings, maybe cyclohexenones. You got these pseudo-eclipsed interactions that get relieved when you do the reduction. Okay. Now, what does this molecule look like when reduced? Well, if you do the lithium aluminum hydride reduction followed by aqueous workup, but let's not worry about the aqueous workup. Let's just do the reduction. Depending on which side the hydride gets added to, let's sort of think about what we've introduced there, right? We relieved an eclipsed interaction. In the structure on the left, what types of, do you see any steric problems we've introduced that weren't there in the starting material? Not really. You got an equatorial oxygen. You've got gauche interactions, but what else are you going to do? Like, there's not. So, and certainly gauche is better than eclipsed. What about here? Right. Now you've got 1,3 diaxial interactions that you've introduced. That's true. But we know that we know how bad those are because we've got A values. We learned about A values in the chapter on conformations. And the A value for, say, an OH group was maybe around 1 kilocalorie per mole. All right. So we're taking two pseudo-eclipsed interactions that are together worth about 4 kilocalories per mole. We're getting rid of those, and we're replacing it with, at worst, a 1 kcal per mole destabilization due to a 1,3 diaxial interaction. So you see overall, by the reduction, we're reducing angle strain. We're reducing torsional strain and getting rid of, it's a net favorable effect. Reduction of torsional strain pays for the introduction of 1,3 diaxial interactions. Okay, so sometimes knowing what some of these numbers are can help you rationalize results. Now let's make it a little bit more complicated. Instead of dealing with cyclohexanone on its own, let's put a T-butyl group there, okay, at the 4 position. T-butyl groups essentially lock the ring in a particular conformation because the A value of the T-butyl group is like 5.5 kilocalories per mole, meaning once you've got the T-butyl group there, you're not gonna switch to the other chair. It's inaccessible. Okay. So now let's do the lithium aluminum hydride reduction. Now we're not talking about rate and which is faster, but we are going to talk about stereoselectivity among the products. Now let's, this is a great time to actually review our homotopic and antiotopic versus diastereotopic. You've got 2 faces to this ketone. Are they homotopic, diastereotopic, or an antiotopic? They're not homotopic. How can you tell?
Because one base is different, but I always forget the difference between diastereomers.
Okay, right. So there's symmetry definitions, and then there's sort of make sense of the products definitions. Either way works. Homotopic would be if you can do the C2 pancake flip and see exactly the same thing, which we clearly can't do because if you flip it, the T-butyl group is now down instead of up. Does that make sense? Okay, so they're not homotopic. An antiotopic would be mirror images of each other. And these aren't either, right? Because you do the mirror plane of the ketone and if this page is the mirror plane, right, what's the reflection of that through the mirror? So they're not enantiotopic either. The other reason you can tell they're not enantiotopic is because if you were to do an addition reaction, the two possible products are not enantiomers of each other. Right? Therefore, they have to be diastereotopic. Okay? So we got two diastereotopic faces, the top face and the bottom face. I'm going to show you the results. Actually, I'm going to let you predict. What do you predict would be the major diastereomer for lithium aluminum hydride reduction of this ketone? And I'll draw the products here. One is where the proton is added from the top face, same side as the T-butyl group. The other is where the proton is added from the bottom face, opposite side, the T-butyl group. All right? So what do you think? Make a prediction. You think the first one's the major product? Okay, Caitlin thinks the second one's the major product. I have to be equally doubtful of both answers so that I don't. Is that what you really think? Would you like to phone a friend? You guys don't even know what that is because that was in the early 2000s on television. And you were not watching Who Wants to Be a Millionaire back then, were you?
My
Yeah,
great grandma watched it.
Your great grandma watched it. Okay. Yeah. Well. Okay. So let's talk about maybe justifications for those answers. Why might you like this answer? Why might you like that answer?
The hydride's attacking first. So with that approach, I think that the second one, if you approach from the bottom, you're getting a little bit of steric strain from those CH bonds.
Okay. So you're thinking about.
Yeah, those.
Okay.
Because those are the closest things and probably what matter most.
Right. I mean, we're thinking about Berge-Dunit's trajectories. So
You gotta approach through.
you've either got that trajectory or this trajectory, A or B. I might want to use A or B for other things. So 1 or 2. All right. If you approach from 2, you've got those axial alpha hydrogens that are you're sort of pseudo-eclipsed with. Maybe that's okay, but potential steric problems. If you approach from 1, you've got those 1,3 sort of diaxial beta protons in your way. Okay, what other considerations?
If we're approaching from 1, maybe the terbutyl group is big enough to influence the.
Right, yeah, so you've got sterics, you've got that terbutyl group, which maybe it's preferred to go opposite the terbutyl group versus towards it. Okay, good. We missing anything? What?
I think the turbulent's too far away.
You think the terbutyl group's too far away? Okay.
For lithium aluminum.
Okay. I mean, actually, there's something you guys haven't said that I'm actually pleased you haven't said.
hyperconjugation.
No. I would be pleased if you were thinking about hyperconjugation. What's that? Product stability. Right. Why do I not care about product stability? Right. This reaction is irreversible. Lithium aluminum hydride reduction is irreversible, so product stability doesn't matter. It is true that having the OH axial is less stable than having the OH equatorial, all other things being equal, but that doesn't matter here because the reaction's irreversible. So the only thing that matters is which product forms fastest, which approach is fastest, not which product is the most stable one. Okay, so This is perfect. Dun, dun, dun.
No.
So that's all we have time for today. Tune in next time when. You want to know the answer?
Yeah.
Yeah.
Okay, I'll tell you the answer. It's 9-1 for the first one. Yep. Now you can congratulate yourselves if you got it right, but we still haven't talked about why. So.
We're still wrong.
So you could have got the right answer for the wrong reason. So we'll talk about it, and if you want to preview, you can look at your text. We'll see who wants to do that.